Hello. Here I will go through a concrete example calculation of composition, or scientifically speaking. Okay, this table of the symmetric group on 3 elements. So that is the group of permutation. That is a set of all permutations of 3 elements. The number of such permutations is 3 factorial, which is 6. So listing them, we can stop when we will have 6 of them. I will list them first as pictures, as their graphs. The identity, of course, is the one to start with. It's the easiest. So here are my 3 elements, 1, 2, 3, for example, and here is another copy of the same set, 1, 2, 3, and 1 connected with 1, and 2 with 2, and 3 with 3. And I could also do a transposition of 1 and 2 and keep a third element in its place. I could do it with 2 and 3, transpose them and keep 1 fixed. I could swap 1 and 3 and 2 will be fixed. So far I have 6 permutations. I need 2 more, and the one of these 2 remaining is, say, moving 1 into 2, 2 into 3, and 3 back into 1, the cyclic permutation of length 3. And we could do it in a different order, so we could move 1 into 3, 2 into 1, and 3 into 2. So writing them as products of independent cycles is another way. I could just call the identity E, because really it will be 3 cycles of each of length 1, cycle of just 1, cycle of just 2, and cycle of just 3, which I don't really need to record because they don't do anything. The second permutation will be transposition of 1 to 2. 3 is fixed, so I don't record it as well. The third is a transposition of 2 and 3. The one after is a transposition of 1 and 3. So these are also cycles of length 2. So here I have a cycle which moves 1 into 2, 1 goes into 2, 2 goes into 3, and 3 is pushed back to 1. And the last one is 1 is going into 3, 3 is going into 2, and then 2 goes back, returns to 1. So these are notations in terms of cycles, and you can see that all permutations of 3 elements are cycles. Well, that is not, of course, true in general. If you look at permutations of 4 things, of 4 elements, you will see non-cyclic, of course. So I will be using this notation. It's more straightforward, sort of more apparent graphical notation for computing the composition and recording the results in positions of this composition table. I will use a different ordering of those 6 elements. I will, of course, start with the identity, make it a bit larger, but then I will just list the 3 cycles, and after that I will list the transpositions. So this is one symbol, of course, and the same order I will use for rows. And now I have to compute results of composition in the following agreement. So this will be the one which is applied first, the row label, and the column label will be the one which is applied after. So for example, computing, say, the composition in here, I'll have to start with this picture, so apply it first, and I will put it on top of what comes after, and that is what comes after. And then we could see that after straightening the lines, the first goes to itself and then the other two cross, so we have a transposition. So that is what we have to record in here. But let me start from the beginning. So the first row and the first column are easy because it's just composing with identity from one side or the other, and that is a trigger manner. And that is just here as well, repeating the elements we compose with the identity. So if one starts here, we have to compose this with itself. Well, check me. Yes, maybe at this point it's good to pause the video and do it yourself and then compare the results. That's always fun. So I will proceed, and my answer here will be this. And yeah, here's my way really. Without computing, I know something about this block. In this block of 3x3 there will be only 3 cycles. Composing 3 cycles, I will end up only with 3 cycles, and hence I can just use the Sudoku rule, so to speak, the rule which says that elements do not repeat in a given row or a given table of a given column of a Kelly's table. So I already have this, I should not have it again, so I should have either identity or this, but identity doesn't is not possible because 3 cycle done twice is not identity, obviously. So identity actually happens here, and it happens here, and here again I can guess what it should be. It should be this element, this 3 cycle. So then following the same rule, if I separate my table into blocks, again I'm doing guesswork, but okay, let me not do it and do it according to the rule. So what supposed to appear here is a result of composing the same 3 cycle, this label, with that transposition of 1 and 3. And again, after straightening lines, the third line 3 goes to 3, and then the 1 goes into 2 and 2 goes into 1. So we have this transposition here. And then again the rule of Kelly's table will say that this has to come up here, nothing else is left in, nothing else is not used yet in the second row. So the same exclusion rule will force this picture to appear here, and here we'll have to have this picture and this picture. And continuing the same sort of generic pattern, you are invited to discover. So in this block you will only see transpositions as in this block. But you cannot really assume that there will be just a mirror version flipped along the diagonal, because it's not true. So we have animals in the video. We have to compose, just computing this honestly, we have to compose this transposition, put it on top of this 3 cycle, and see what happens. And now we have 2 goes to itself, and then 1 and 3 change places, so that is this transposition now. And again, exclusion rule will force this to happen here, and to compute what happens in here. Yeah, maybe doing it honestly, so we have yeah, we could guess what could happen, say, in here, because not very honest apparently, because We already have this symbol, we already have this symbol, so only one transposition which is left is this, and so we should have here we should have this transposition, and then inevitably this here, and 1 and 3 transposition in here. So now composing transpositions. Every transposition is its own inverse. You could see it, well, it's just pure logic. So you transpose 2 elements, you transpose it again, you do nothing. So the diagonal answers in this block are all identity symbols. And say composing these 2 transpositions, let's compute it again. So we have, maybe I'll compute it below the table. I'm composing these with the transposition 1, 3. So this moves 1 into 2, 2 into 3, 3 back to 1. I have this recycle. And the rest I can guess now, so this will be the recycle which I haven't used yet, so that will be this recycle. Here I should have this recycle, and then this here, this one here, this one here. Please check it. Every answer can be verified using honest computation of putting this on top of that, for example, and straightening lines and seeing this answer. So that is the composition or Kelly's table of the group of permutations of 3 things. Again, what is special about this particular ordering, when 3 cycles come first and transpositions come later, is that we have a clear sort of block pattern of the results. 3 cycles compose with 3 cycles into 3 cycles, with transpositions they compose into transpositions, and with transpositions with themselves compose into 3 cycles. So that looks supposed to look familiar. It looks like a pattern of even here and odd here. So if this is even or this is odd, and this is odd, then even with even is even with odd is odd, and odd with even is odd, and odd with odd is even. Or if you like to multiply, because yeah, it's more close to composition sign, you could think of this as positive or sign plus, and this is sign minus. So anyway, we have this clear pattern separating our group. So we'll look at the generic situation of the same behavior in the next video. Another thing to observe is that, as I said before, the table is not symmetric with respect to the main diagonal. So, for example, these 2 entries are different, which is saying that the composition is not commutative. And, well, it is commutative in this block, but not in general. So if we say, compare these entries, what do we compose in here? So we compose a 3 cycle with the transposition one way, or the other way, the same 3 cycle, and the answers are different. So that is a manifestation of non-commutativity. The group is this set with the operation of composition, which is a group, is non-abelian, the technical term. So that is probably enough for this little example. I'll see you later with more.